Hello. Another interesting use of geometric series is to rationalize a recurring decimal. So we all know what a recurring decimal is. We dealt with them way back in first year. A third would be written as 0.333 going on forever. And how do we write that in a more abbreviated form? We'd say it was 0.3 with a dot on the top of it. So that's our recurring decimals. If we take a situation like this where we have two dots, what does that mean? It means that we can write this approximately, so squiggly brackets for approximately, sorry, squiggly equal sign for approximately, 0.257575757, continuing on like that forever, repeating our 5 sevens over and over and over again ad infinitum. So the dots over both of the numbers mean that this is the beginning of the recursion, this is the end of the recursion. So this is what our number looks like, and you can be asked to rationalize it, or you could be asked to write it in the form a over b, which is the same question, just written in a slightly different way. What we have to recognize here is that we effectively have two slightly separate situations going on. We have a 0.2, which isn't really anything to do with a series, and then we have plus 57 over something, plus 57 over something, plus 57 over something, plus 57 over something. So we have a series of 57s. There's a pattern that we can write for connecting this 5-7 repeating itself over and over again, and it's as follows. This first 57 here is, as a fraction, would be 57 all over. How many places do I have to move my decimal point? 1, 2, 3. So over 1,000. The number of zeros tell you how many decimal points we've moved, if we remember this. For the next 57, we have to go 1, 2, 3, 4, 5. So we have to go 5 decimal places. So it's going to be 100,000. 1, 2, 3, 4, 5. And we would continue on that pattern forever. So I now see that I have a series going on here, going on forever. So an infinite series going on this way, and I have just some constant added on to that. This business where we have to take a number or take a situation and break it up into some constant plus a series will come up again in more advanced questions in areas like financial maths much later on. So you need to be aware that this is something that can happen. Now, recognizing that we have a geometric series because we're dividing, I can see I'm dividing by 100 each time to get between the terms in my series. I'm going to say my first term in my series is 57 all over 1,000. And my common ratio is going to be Tn all over Tn minus 1 is equal to 57 all over 100,000 all over 57 all over 1,000. When I put that in my calculator or rearrange it, I will get that that is equal to 1 all over 100. So I now have my common ratio and I have my first term, and I remember that I'm adding on 0.2 to this series. So the value of this is going to be 0.2 plus my sum to infinity. And I know my sum to infinity is on bottom of page 22. Sum to infinity is equal to a all over 1 minus or. That's going to be equal to 0.2 plus a is 57 all over 1,000. 1 minus 1 all over 100. I put this into the calculator and I will get the fraction 19 all over 330. And I add these two together, and on my calculator I will get 17 all over 66. Now, one of the ways you can check whether you've done these questions correctly or not is if you press the S and D button on your calculator to convert that into a decimal, it will give you 0.257 recurring. So you can very easily check that you've done questions like this correctly using your calculator, because the fraction that you end up with at the end, the rational number you end up with at the end, the fancy name for a fraction is a rational number, and also can be written in the form a over b. So you can check on your calculator using the S and D button whether you have done your steps correctly, because the calculator should be able to convert this back into a decimal and give it to you in exactly this form. And that is all you need for being able to deal with recurring decimals.